Okay, so you guys last week bounced some balls, right? So we're going to be studying momentum. This lecture will help you understand momentum, impulse, conservation of momentum, and collisions. Today we're going to be covering 3 of those topics, which is momentum, conservation of momentum, and collisions. We're going to save impulse for Wednesday. What is momentum? There's some pictures to think about. What has more momentum? Now, first of all, let's look at these pictures. How fast is that? What does that truck look like? It's on a freeway. What does it look like it is?
On the street.
Do you think it's on a street, or do you think it's parked? What do you think? What? It looks parked to me. If it was parked, let's assume that it's parked, okay? Which has more momentum, the snail or the truck? The snail, right? Because the truck, if the truck is parked, does it have any momentum? No. And the snail is like cruising on a race, right? So the snail's moving. If the truck were moving, which would have more momentum? The truck. Okay. Which of these do you think has more momentum? So yeah, so you have to make certain assumptions, right? So if you're assuming that the red one's going faster, then you could say that the red one's going. For sure it's the red one. Okay. So yeah, so momentum relies on 2 things. It relies on mass and on velocity. So here's our equation for momentum. Okay, momentum is mass times velocity. It has to be moving in order to have momentum. You can also call it inertia. Ooh, that's okay. Just woke everyone up. It's inertia in motion. Okay, and the units for momentum, mass is kilograms, right? Velocity is meters per second. So for momentum, it's just kilograms times meter divided by second. That's the units for momentum. It's no new fancy units. Okay. So these are just examples to conceptually think about. If you had a boulder and a stone rolling down a hill at the same speed, the boulder would have more momentum than the stone. Okay. The bottom picture, it's assumed that the boulder on the left is going faster than the one in the middle, and the one on the right is stopped. So the one on the left would have the most momentum, the one in the middle would have less, and the one on the right, if it was stopped, would have no momentum, right? A moving object, does it have momentum? Yes. Does it have energy? Does it have speed? This would be all of the above. So our equation for momentum is P equals mv. P being momentum. This is a symbol for, I don't know why they use P, but P is a symbol that they use for momentum. So it says when the speed of an object is doubled, what happens to its momentum? It doubles. Very good. Okay, there's 2 different types of collisions. All right, when we were bouncing balls and stuff last week, were some more elastic than others? Okay, so how did you know that one was more elastic than the other? Because it would bounce back, it would retain most of its energy, right? Okay, so a completely elastic collision occurs when colliding objects have no kinetic energy loss. Do you know what kinetic energy is? Kinetic energy is energy of motion, okay? So when there's no loss of your energy of motion, there's no heat loss, and there's no damage. Now, we live in a very friction-full world, so it's hard to have a completely elastic collision, but you could say something is mostly elastic, right? The pool, like playing pool, is a good example of a mostly elastic collision. And the other kind of collision is inelastic collisions, okay? Those occur when colliding objects have energy loss or generate heat or have deformation. And a lot of times the objects end up sticking together, okay? Now, a lot of collisions are kind of in the middle. So I'm actually going to show a little video and we can try to like guess which collisions are more elastic versus inelastic. Let me. Here we go. There we go. Can you guys see okay? So here we go. Okay. Top 10 sports collisions. Number 10. Okay, more inelastic or elastic? It's a little bit in the middle. I would probably say slightly more inelastic, but ooh, I would say that was inelastic. Watch this one. Ooh, that one was kind of elastic because he bounced off a little bit. There's another like semi-elastic one, right? He was uninjured. I'd say that's an elastic one. Yikes. She was fine. There's another one that got hit. This bike crashes are awful. Oh. Ooh. That's not pretty. I bet you there was injuries on that one. I would say that's more inelastic. Oh, definitely. Lots of damage. So the first, when the first gets hit, it's kind of elastic because he kind of bounces off, and then it was more. Ooh. So you can see, like, sometimes it's harder to like realize. Now, if you did like a train crash in a car, that's an obvious inelastic one, right? Or like bouncing a ball, that's, you know, more elastic than inelastic. So those are some examples of different kinds of collisions. That one, well, there was definitely deformation, but there was also a lot of bouncing, right? Yeah, I might classify. What would you say? Elastic? Yeah.
Like, I think there was like a couple crashes.
There was definitely multiple crashes, so there would be multiple things to talk about.
The car against the car, I think, was and the car against the ground is inelastic.
Gotcha. Yeah. So we're going to be doing a lab, and you're going to have to, the reason I wanted to kind of talk a little bit about that is I wanted you guys to be thinking about, you know, rarely do you find a perfectly inelastic or perfectly elastic. So a lot of times it's harder to figure out. Okay, so I think, okay. So now there is a worksheet in Schoology that's due by the end of the period. It's a pretty short one. It's on momentum. I want you guys to do that. Make sure you understand that before we move on to conservation of momentum. Then we're going to lecture some more, and then you'll do another worksheet for homework. Okay, coming back to the lecture, because I want to have as much time for you guys to work on your next worksheet, which is a little bit more complicated. Anyone have any question on that one? As usual, I posted the answer key for you to check your work. Okay. Anyone? If you didn't finish this worksheet, you will have more time after I finish the lecture. Okay. All right. So next. Sorry, my screen freezes from time to time. Okay. All right. So imagine you have two football players. Do you have any football players in here? Football players? All right. So imagine you have two football players and they're running towards each other. Okay. And so what happens to a football player's momentum when he's hit by a defender, and what happens to the defender's momentum? All right. For all collisions in the absence of external forces, the net momentum before the collision equals the net momentum after the collision, okay? So if you don't have any friction or any external forces involved, you're gonna have what's called conservation of momentum, where all the momentum that if you add it all up before a collision is gonna be equal to all the momentums added up after the collision. Does that make sense? So we can go down here to, sorry, the law of conservation of momentum. In the absence of an external force, the momentum of a system remains unchanged. Okay? An example, when a cannon is fired, we learned from Newton's third law, right? The cannon puts a force on the cannonball, right? And the cannonball has a force on the cannon. Okay? The cannonball gains momentum while the cannon gains an equal amount of momentum in the opposite direction as the cannon recoils, right? Okay? Remember that velocity is a vector, not a scalar, which means direction matters. In this case, one velocity is positive and one is going to be negative, okay? So in that situation, when you have a cannonball inside of a cannon and it's just sitting there at rest before it fires, what's the momentum of that system? Zero, exactly. And then after it fires, you have a cannon going one direction, and so it has momentum that way. And the cannonball has momentum one direction, and the cannon has momentum the other way. And those two momentums are going to be equal and opposite. So that whole system, if you added the equal and opposite, that would be zero. So our initial momentum is equal to our final momentum. Yes, Brandon?
This one's not moving, this one is, but it just stops on the wall. Like, how would you like?
Then that means there would be an external force. That if it was an example of, so Brandon said, what if you had like a block that was still and another block that had momentum and it was cruising along and it hit it and then they both stayed still? So one of two things would happen. One is that one block is so massive that the other block, basically the movement afterward would be so insignificant. But basically you have, in that situation, you're gonna have an external force, which is friction, that's preventing something is gonna, you would have to have some movement afterwards because the momentum,
Be so little that it's like,
yeah, insignificant. That make sense? Good question. Okay, if there is friction or other outside forces, then the momentum can either be reduced or increased depending on whether that external force is slowing it down or speeding it up, right? Okay, so if we look at that in equation format, here we go. Here's our equation format. We have the net momentum before a collision equals the net momentum after a collision, okay? Another way of writing that, you could say the sum of the momentums initially is equal to the sum of the momentums finally, like after the collision. Make sense? So here's a particular example. Okay, so here you have a single car moving at 10 meters per second, and it collides with another car of the same mass, which is at rest. So if we draw this out, we have a single car moving at 10 meters per second, and you have another car, basically at a stoplight or whatever, at 0 meters per second, right? Then they collide, okay? So, and assuming if it's an inelastic, let's say the cars stick together, what would their velocity be after the collision? Okay, so here, the momentum of the first car would be mass, which is m, times the velocity is 10, right, in that direction. Plus over here, mass times 0. So the initial momentums would just be, we can eliminate this one because it's 0. So the initial momentums would just be 10m, right? Now over here, we have mass times velocity plus mass times velocity. Assuming it's the same velocity, we can use the same v, right? Make sense? So mv plus mv would just be 2mv. So down here you can see we have 10 meters is equal to 2mv. You divide both sides by 10m, and you get an answer of 5 meters per second. And we're going to go through a couple other examples, okay? If you had a different situation, I'm going to do, imagine if you had one car going this direction and another car going this direction, right? Then when you added these up, you would have, let's say this is, just to make this easy, we'll just say that this has a mass of 1 kilogram and a velocity of 10 meters per second. And we'll say this has a mass of 1 kilogram and a velocity of 5 meters per second. So looking at this, the momentum of which direction are we going to call positive? I usually say positive is right, but it doesn't matter as long as you're consistent, okay? So here we have mass times velocity here would be 1 times positive 10, right? Over here, this would be mass times, to find the momentum of this car, it would be 1. Would this be positive or negative 5? That would be negative 5. So if we wanted to know what the total momentum of was before the crash, this would be 10 minus 5, or 5 kilograms times meters per second. Make sense? So you have to you have to pay attention to direction. Okay?
Wait, so for that equation where it's net MV before, is it net MV before equals net MV after, or net MV before plus? Like, what is that equation?
Oh, okay. So this one, in this particular scenario that I just drew, it was before collision. I was just showing you the positive or negative. But the equation is your net MV before collision equals your net MV after.
Okay, so the demonstration that you were just doing was for before, like, the collision
Yeah.
happens.
So then there would be another scenario. There would have to be more to this problem. On this right here, I was just merely illustrating that you have to pay attention to positive and negative.
Oh, okay.
That makes
Alright, that
sense?
makes sense.
Good question. Okay, so I'm going to